Bon après-midi, good afternoon. I must start by thanking very much the organizers, and in particular my friend Benguerir for inviting me here. My wife and I are delighted to participate in this meeting, which in my experience is absolutely unique among the many meetings on complexity where I've spoken. I have never seen so many distinguished speakers gathered in one place, and such a breadth and depth in the presentations. So my wife and I are delighted to be here at this meeting, and we're also delighted to be in Morocco for the first time, and in fact in Africa for the first time. So thank you very much for including us in this event. Okay, so now for something completely different. I'd like to talk about something much less important than the topic of gender equality. I'd like to talk about metamathematics. Now, you may ask, what is metamathematics? That's a good question. It's a mysterious subject. I actually like to move around.
La régie, vous pouvez brancher le...
Yeah, I like to move around. Hello, can you all hear me? Okay, so what is this mysterious topic called metamathematics that very few people have heard about? Well, metamathematics is a part of mathematics, but it's sort of self-criticism. It's an attempt to psychoanalyze mathematics using mathematical methods. And it's a relatively little-known field. I'd like to give you an overview of this field as I see it. We also have here Stephen Wolfram, who has just very recently developed a radically different view of metamathematics, and I hope he told us something about it yesterday, and maybe during the roundtable he'll say some more. So this field has a history. I just want to mention, I'd like to say that Leibniz is the, the grandfather of this field, but maybe the father of the field is David Hilbert, and some famous names who worked in this area, famous and non-famous, are Gödel, Turing, and Post, who is less known. Just thought I'd mention their names. So I want to try to give you a sort of, I say, some key ideas, about what metamathematics is and what it can accomplish. So, the main object of study in metamathematics is something called a formal axiomatic system. It could also be called a formal axiomatic theory. And what is that? Well, you see, if you want to study mathematics using mathematical techniques, how do you do it? Well, you need a sort of a frozen version of mathematics that you can look at from outside, from above, that you can study. And such a frozen version of mathematics, crystallized version of what mathematics is called a formal axiomatic system, or a formal axiomatic theory would be better, but... And what is it? Well, it has a number of components. You have a finite set of axioms, you have rules of inference, which are logic, the logic that you're using. The axioms are your postulates, the principles that you start with, and then the idea is to make deductions from the axioms using the rules of inference. And what's unique about a formal axiomatic theory is that the whole system has to be set up so precisely that there are no subjective elements. In fact, it has to be done so precisely. Well, you're going to use, as I say there, it's a language. You're going to be doing mathematical proofs. You're going to be doing mathematics in an artificial language. It's not a programming language. It's a language for reasoning and proving mathematical results, mathematical theorems. And it has to be very precise. So you're not going to use a human language. You're going to be using symbolic logic. The grammar and syntax are specified very precisely. And in fact, the whole thing has to be set up so precisely that there is a mechanical procedure to check if a proof is correct or not, if it satisfies the rules. So the idea is that there is no subjective element. This is a completely objective system, and it's very precise, and you can stand outside it and look at it and ask, how well does it do? What can it accomplish? And that's the meta-mathematical part, that you're outside this looking at it and studying it. So what is the real idea? The goal of all this idea can be traced back to Leibniz and probably further back, but it was Hilbert who enunciated the goals of metamathematics most forcefully. And the idea is that he assumed, it's usually thought, that if there's one area of human knowledge which gives absolute certainty, that area is mathematics, absolute certainty. And the idea is that mathematics is completely black or white, or can be, if you do it with a formal axiomatic system. There's no subjective element, it's completely objective. And Hilbert's goal, in fact, was to, well, there had been paradoxes and controversy about mathematical methods before Hilbert. And Hilbert's goal was to settle this all once and for all, proposing one formal axiomatic system for all of mathematics that all mathematicians could agree on. And then in principle, there would be no longer any doubt about whether something could be proven or not. This would capture all of mathematics truth, and it would show, if you could do this, you would be showing that mathematics, if you could have a formal axiomatic system for all of mathematics, that would in fact show that mathematics does give absolute truth, because it's so precise that there's no uncertainty about whether a proof is correct or not. So this was the idea, and this is how metamathematics starts, but there were a few surprises along the way. First, let me give some examples of formal axiomatic systems or theories. Well, a very nice one, very well known in is Euclidean geometry, but done much more precisely than in Euclid. And Hilbert and then Tarski finally completely formalized geometry and made a formal axiomatic theory for geometry. It's not very well known. Tarski did some very good work in this area that somehow slipped between the cracks. Now, another better-known example of a formal axiomatic theory is something called Peano arithmetic. It's just number theory. It's 0, 1, 2, 3, 4, 5, the natural numbers, the positive whole numbers, well, the non-negative whole numbers. And you just have addition, multiplication, equality. It's a very simple system, and it includes what mathematicians refer to as number theory, or arithmetic is the older name. And that system was studied a great deal in metamathematics, as a matter of fact. But a more powerful system is called Zermelo-Fraenkel set theory. Set theory starts with Cantor, but is finally formalized by the work first of Zermelo and then of Frankel. So this is called, it's ZF to its friends, and this is a theory which contains a lot more than the non-negative integers like piano arithmetic. It's a much more powerful system. You can develop, I don't know, a lot of mathematics in it, and there are newer examples. So this is the kind of beast that metamathematics wants to study. So now, this notion of a formal axiomatic system or a formal axiomatic theory it was Emil Post who said most clearly, gave a more abstract definition of a formal axiomatic theory. In his work and in my work, the details of what goes on inside the formal axiomatic theory are not important. I don't really care what kind of logic is used in the theory, what are the rules of inference, what are the axioms. It's not, one famous practitioner of metamathematics was Kurt Gödel, and his work, he really needs to go into the bowels of piano arithmetic and take advantage of what's there. And in Emil Post's approach, as in my own, we're flying in an airplane in the stratosphere very high above the formal axiomatic system, so high that the details sort of disappear at that altitude. And let me tell you the essence, what Emil Post, following Turing actually, and I follow Emil Post, perceived as the essence of a formal axiomatic theory. Well, this diagram, formal axiomatic system, goes into a computer and out comes an infinite set of all the theorems that can be proved within that formal axiomatic theory by making all possible deductions using the rules of inference, using mathematical logic, from the postulates or axioms that are at your initial principles. And the idea is that you run through all possible proofs, you check which ones are correct, which is mechanical, can be done mechanically because formal axiomatic theories, when they're formalized, are very, very precise, and there's always a proof-checking algorithm. So you run through all possible proofs in the formal axiomatic system, you check which ones are correct, and that way, in principle, but not in reality, you can generate or calculate or enumerate all the theorems, everything you can prove in this theory, mechanically. There's an algorithm for doing it. So this is the abstract view of what is a formal axiomatic system. It's just an infinite calculation which is going to produce the set of all the truths, well, all of the theorems that you can prove within the system. Okay, all the statements which are provable within that system. So this is the object that metamathematics studies. And you can forget what the meaning of the axioms are. You can just look at it from outside. Okay, so I'd like to introduce a notion of complexity, since we're at a meeting on complexity. I think the work that I've devoted my career to has been applying complexity in metamathematics, a notion of complexity. The idea is to measure how big the formal axiomatic system is, how powerful it is, put it on a scale and weigh it, and here's the way I do that. So I don't need to know what's happening. Remember, the formal axiomatic system, according to Emil Post, is just an algorithm for generating all the theorems, for calculating one by one all the theorems. So this algorithm can be programmed out in some programming language, and then the question is, look at the size of this program. How big is the software implementation of this formal axiomatic system that runs through all possible proofs? This is a computation that goes on forever. It's very slow, but in principle, it can be done if you have a formal axiomatic system. And what interests me is how much software you need, the size of the software implementation of the formal axiomatic system, and I like to measure it in bits rather than bytes or kilobytes or megabytes. So I define the complexity of a formal axiomatic system to be the size in bits of the program that generates, enumerates all the theorems of the formal axiomatic system, and it does this by running through all possible proofs and checking which ones are correct. The tree of all possible deductions from the postulates using all possible applications of the rules of inference. Okay, so let me emphasize this is an infinite computation. This process never stops. It goes on forever, looking for bigger and bigger proofs, looking through bigger and bigger proofs for theorems that require bigger and bigger proofs. And it's going to be very slow, and it's never going to stop, and I don't care. I'm a theoretician, okay? So I know that most of you are very interested in practical applications, and we've heard a lot of fascinating stuff here about politics, sociology, all kinds of things. But I'm a pure mathematician, and this is the game I play is a little different, okay? This adds to the variety, the diversity of topics covered here at the conference. Okay, so this is going to be the key thing, to measure the power, the complexity of a formal axiomatic system by the size in bits of the program that calculates all the theorems one by one, very, very slowly. But that doesn't matter, okay? I'm only interested in how many bits, in the amount of information. I don't care about the time. Well, that corresponds to the size of the proof, actually. Okay, so this is the key tool that I'm going to use, this notion that Post didn't use. This is adding something. And I'd like to also introduce another concept, which is, Euclidean geometry looks at diagrams of triangles and circles, right? And peano arithmetic talks about addition and multiplication, prime numbers, all that kind of thing. Well, the question that I want to consider is the problem of proving that programs are elegant using formal axiomatic systems. Now, you may ask, well, you know what a program is, right? It's a computer program. But what is an elegant program? Well, I'd like to call a program elegant. There's something funny going on the screen. Well, definition of it, let's see. C'est la vie. An elegant program is one that has the property, it's the smallest program to calculate what it calculates. More precisely, a program, I like to call a program elegant if it has the property that there is no program written in the same programming language that's smaller than the program we're considering that produces exactly the same output. I don't care if it's faster, if it's slower. All I care that it produces the same output. So an elegant program, in other words, is the smallest program for getting the results you want, but there may be several, which is why you have to, there may be several elegant programs, which is why you have to define it this way, okay? So this is not a practical notion in the world of software writing, because the most elegant program would be rather cryptic, and I used to work as a computer programmer for a living, and the last thing people who pay programmers want is a program that is incomprehensible. So elegant programs, in fact, except if you're running a programming competition, are not of great interest. But sometimes people in a contest try to write the most concise program for something, and that can be fun. So this is the question that I'm going to consider, which is using mathematics, or more precisely, using formal axiomatic systems, formal axiomatic theories, to try to prove that programs are elegant. Now, there's some few facts about elegant programs you should know before we we jump into this. Okay. Well, I can see perfectly the slides. I'm sorry that you folks can't. Well, the facts about elegant programs, the key facts is there are infinitely many elegant programs because there are infinitely many outputs that you may want to write a program to calculate. Now, as I said already, for every possible output of a computer program, finite or infinite computer, with finite or infinite runtime, there's at least one elegant program. There may actually be several if there's a tie. And also, there are elegant programs that are arbitrarily big because there are infinitely many outputs that you may want to get from a program, so you're going to need infinitely many programs to do that. Okay, so there are lots of elegant programs out there, tons of them. And what I'd like to consider is the problem of proving that a program is elegant, that you have a particular program in your hands, a specific program, and can a formal axiomatic system prove that a program is elegant, that an individual program is an elegant program? It turns out this is very, very hard to do. It's extremely hard to do. And in fact, it's so hard to do that you can prove an incompleteness theorem. There's a famous incompleteness theorem due to Gödel in 1931, and Turing in 1936 found a different path to incompleteness, and Emil Post also. But here is yet another path to incompleteness, and the assertion is that formal axiomatic systems, are very limited in their ability to prove that individual programs are elegant, to exhibit provable examples of provably elegant programs. And and the reason is, here's the key result, that you can't prove that a program is elegant if the size of the program in bits is substantially larger than the complexity of the formal axiomatic system you're using to attempt to prove that the program is elegant. And remember, the complexity of the formal axiomatic system is also measured in bits. It's the size in bits of the program that runs through all possible proofs and generates all possible theorems. And you want to use the same programming language, by the way, for both the program that you're trying to prove is elegant and for measuring the complexity of the formal axiomatic system. It's important that you pick one programming language and stick with it throughout the entire discussion. And if I were giving a course on this, I would give more information about the programming languages that are good, but we don't have the time. Okay, so this is the key result. And let me point out that this is in some ways, disconcerting, pessimistic, unpleasant incompleteness theorem. And it sort of drops out when you start considering this notion of the complexity of a formal axiomatic system, and when you start asking about, can you prove that a program is elegant? So why is this disconcerting? Well, to Hilbert, it would have been very disconcerting because he wanted to put mathematics on a firm footing by finding one formal axiomatic system for all of mathematics that everyone would agree on, and then you would have very tangible, concrete evidence that mathematics, if it could be done in principle in that way, not in practice, provides absolute certainty. This was Hilbert's goal. But if you have incompleteness, if no formal axiomatic system can capture all of mathematical truth, well then, you have to keep maybe changing your formal axiomatic system, and where do you get a new formal axiomatic system from? That got rid of certainty. People can argue about whether the new formal axiomatic system, whether its postulates are correct or self-evident or intuitive. They can argue about the rules of inference. This pulls the rug out from under Hilbert's proposal to get all mathematicians to agree on the rules of the game for pure mathematics, which is very unfortunate. So using a term that was not in Hilbert's time, but physicists like to use, there is no theory of everything for pure math. That's what incompleteness result shows, starting with the famous 1931 incompleteness theorem of Kurt Gödel. And not even if we restrict ourselves to what looks like a not particularly important mathematical question, which is whether or not programs are elegant. Okay? So I should say a little more. You know, you may say, what do I care about whether a program is elegant or not, right? Well, why take this whole approach? Well, the reason I think that this approach is interesting is because it's very different than the traditional approach, Kurt Gödel, 1931. The traditional approach is that Gödel took, he went from this statement is false, which is a paradox, to this statement is unprovable. And he managed to construct a statement about the whole numbers in Peano arithmetic, which says of itself that it's unprovable. Therefore, it's true if and only if it's unprovable, and that shows incompleteness, an assertion about the whole numbers that escapes the power of Peano arithmetic. Now, that involves this notion of self-reference. I'm unprovable. You know, what I'm saying now is false becomes I'm unprovable. And that looks a little bizarre, that self-reference. Gödel manages to carry it out, but it's the assertion that Gödel constructs that's true but unprovable is a little strange because of the fact that it's saying I'm unprovable. Now here we have a different path to incompleteness that I submit is in some ways more fundamental than the Gödel's path to incompleteness, involving complexity rather than self-reference. And as a personal anecdote, in 1974, I was living in Buenos Aires, and I visited New York and took a chance. I called up Gödel on the telephone, and he answered, believe it or not. And I said I would love to talk to him. I was fascinated by Gödel's incompleteness theorem, and I had a different approach based on, I had a different approach that I wanted to visit him and discuss with him. And he said, well, send me a paper of yours, and I'll see whether I give you an appointment. And he gave me an appointment. So there I was, about to start out to travel from Yorktown Heights in New York to Princeton, New Jersey, to the Institute for Advanced Studies. And it snowed. There was a snowstorm. And Gödel's secretary called me up and said that Gödel was very careful about his health, and since it had snowed, it wasn't, an immense amount of snow. But anyway, Gödel canceled our appointment. He wasn't coming into the Institute that day because of the snow, so I never got to visit Gödel and talk to him. So I'm telling you folks what I wanted to tell Gödel in 1974. Obviously, I've polished it up and improved it a little bit in some ways, but the basic message is that. So that's why I think these ideas are interesting, because they provide a different and perhaps more fundamental path to incompleteness. Now, how do you prove this result, this incompleteness result? Well, it's fairly easy. There is no self-reference. This is the outline of the proof. One would have to present it in more detail. The idea is the following, basically. I want to show you that you can't prove that a program is elegant in a formal axiomatic system if the program is substantially larger than the complexity of the formal axiomatic system. So how do you do this? Well, I'm going to assume the opposite and derive a contradiction. So That's called a reductio ad absurdum proof, reduction to an absurdity. So the idea is, consider an object that I sincerely hope does not exist, but I'm going to suppose it does, which is the first provably elegant program, P, within the formal axiomatic system that is n or more bits larger than the complexity of the formal axiomatic system that we're using to prove that P is elegant. Now, what do I mean by the first provably elegant program? Well, what I mean is, remember, according to Post, a formal axiomatic system is just a black box which is putting out a theorem one by one. So as you're generating all the theorems of the formal axiomatic theory by running through all the proofs, you're looking only at theorems which assert that specific programs are elegant, and the moment you find that you've proven that a program is elegant and the size of this program is n or more bits larger than the complexity of the formal axiomatic system that you're using to prove that programs are elegant, then you stop. And what you do to get the contradiction is you realize that this is actually impossible. Why? Well, because this gives you a much more concise program to calculate the same output. How? Well, first of all, if you can calculate, I said it in words, the first provably elegant program that is n or more bits larger than complexity of FAS. But if you program this, how big is the program? Well, it has inside it the algorithm for generating all the theorems, that's complexity of FAS bits, and you need to know the number n, and to write n in binary is about log 2n bits, but you need to double the bits or something, do something, because you're going to put all these bits together and you need to then be able to separate them. So let's take 2 log 2n bits, because we're going to double all the bits of the binary for n and then put a pair of unequal bits, and then we can concatenate that way of expressing n with the program to calculate the formal axiomatic system, and we're going to need a main program that does this process of running through all possible proofs looking for P, and that's going to take C bits to program out. So the whole result is that we've got a program, and once it finds this first provably elegant program, P, what does it do? Well, you can run P. You simulate the universal computer or whatever. You run the program P that you've proven is elegant, and you start, this program that I'm describing, its output is going to be the same as the output of P. But this program, if n is large, cannot exist, because this is a more concise program than the one that you prove supposedly is the most concise possible. You see, because for large n, well, for n not terribly large, the size of this program is going to be less than what you proved about this program. Than the size of the program that you proved is elegant. Its size is going to be at least n plus complexity of FAS, and that's impossible. You found a smaller program that calculates the same output as something that you've proven is elegant. Now, there's a tacit assumption here, of course, which is very important, that I've been assuming that within the formal axiomatic theory in question that we're studying, if you can prove that a program is elegant, then it is in fact the case that this program is elegant. Otherwise, the proof doesn't work. In other words, I'm assuming that the formal axiomatic system only enables us to prove true theorems, okay? That's important. So, now I'd like to look at the converse. At the other side of the coin, we used complexity to get an incompleteness result. So there's this low bound on the size of programs that you can prove are elegant, okay? But let's look at the other, that comes from you thinking about the complexity of the formal axiomatic system. But let's look at the converse, at how well we can actually do. The idea is if we increase the complexity of the formal axiomatic system, maybe we can prove that more programs are elegant and get up to the bound in the incompleteness theorem. And the answer is you can, by increasing the complexity of the formal axiomatic system in the right way, we can get right up to the limitation in the incompleteness theorem. So here is the completeness theorem, that's the other side of the coin, for elegant programs, which is that there's a formal axiomatic system which is basically just has complexity n bits of complexity, which enables you to exhibit every elegant program up to n bits in size, which is to say get right up basically to the limit imposed by the incompleteness result. So this is a concrete example that of how by increasing the complexity of the formal axiomatic system you can accomplish more. Now, you can also increase the complexity of the formal axiomatic system and not accomplish anything if you add axioms that are not powerful enough to really buy you anything. But let me show you how it works to do it right. So there is one axiom, there's one thing you need to know to be able to determine all the elegant programs up to n bits in size. And that's basically to know the n-bit program Q that takes the longest to halt, has the longest runtime, you see. Because if you know that program, you run it, you see how long it takes to halt, and then you run all the programs up to n bits in size for that amount of time. And that will give you all the programs that halt up to n bits in size. And if you know that, you can see which are the smallest ones. But you have to run all those programs up to n bits in size at halt. Well, you've done that using the fact that you have a bound on how long a program can run before halting. So that way, if you get up to that bound and the program hasn't halted, you can forget about it. So once you've found all the programs up to n bits in size that are about 2 to the n of them that halt, in the process, you've run them all, and you can see. Have you run them all? Well, you run them all and you see the output they produce, and that way you can find the smallest program that does everything for programs up to n bits in size, okay? So this is the axiom. This is the piece of information you need to know to be able to deduce which programs are elegant up to n bits in size. Now here there's also there are always technical details, right? The general idea of a proof is usually simple, but then the devil is in the details. And the detail here is what's here. It may be that the program less than or equal to n bits in size that takes the longest time to halt has less than n bits. Actually, it can't have much too less, but that's another, you have to prove that. So just in case this is and you need to know n as well as the longest possible runtime to find all the elegant programs up to n bits in size. So if the program Q that takes the longest time to halt is actually less than n bits in size, you need to pad it in some way so that by looking at the padded version of the program, you pad it to n bits with padding that you can identify and remove, but that gives you the value of n and the longest possible runtime, and then the proof goes through, okay? That's a technical detail. Okay, so up to now, I'm very sorry. I apologize for the technical mathematics, but I'm a mathematician. What can I do? I like to prove things. So those are two theorems we've seen, an incompleteness theorem and a completeness theorem having to do with using formal axiomatic systems to prove that individual programs are elegant. Now, what does this all imply? I think this has some philosophical implications, although we could discuss that. In fact, I think we are going to have a discussion after my talk. What does this all mean? You know, with Gödel's original proof, I'm unprovable, you know, that was very shocking at first, but then people said, well, this doesn't have anything to do with the kind of the people I'm talking about are mathematicians, working mathematicians. Gödel's incompleteness theorem doesn't have much to do with the theorems I'm interested in proving, right? I don't want to prove that I'm unprovable. So there's a question of how seriously one should take incompleteness. Does this really destroy Hilbert's program? Does it really pull out the rug from mathematical certainty? Does it mean we should be doing mathematics differently? Because the formal axiomatic system is still a religion in pure math. It's a kind of a religious dogma. It's also a practical tool, because there are some very good formalizations of the normal mathematics that, well, the mathematics that contemporary mathematicians are doing. In fact, some of the very powerful mathematicians have worked or demanded such systems because they were unsure if some of their proofs were correct or not. And they wanted to put it into a formal axiomatic system where you could check that the proof was correct. They found this reassuring. So there is very good work that continues to build on the idea of a formal axiomatic system, in spite of Gödel incompleteness. Well, anyway, to run to the bottom, to my conclusion, won't have time to justify it. Imre Lakatos has a paper where he coins a beautiful term, which is quasi-empirical mathematics. He says mathematics is quasi-empirical. And what exactly this means? Well, it means it's not theoretical physics by any means. It's not an experimental science. But maybe it's not as radically different from an empirical science as people might think. At least that's the way I would put it. Well, Vladimir Arnold, who was a fine Russian mathematician that I bumped into at a copying machine in the University of Paris once, he put it in a very colorful way. Here you see it. He said, math is just like physics, except the experiments are cheaper, because you use a computer instead of having to have a physics lab full of large, complicated, temperamental, expensive equipment. That's how he put it. So I'd like to talk a little bit more about this viewpoint that I believe in, but of course and Vladimir Arnold seems to be living in, and Lakatos, but they're not here to discuss it anymore. I'd like to talk a little bit more about this viewpoint, which is, I think, definitely a minority viewpoint in the world of mathematics, and even in the, well, not, okay. So another way to put this, mathematics is quasi-empirical, is to say that you believe in experimental mathematics. And there are a number of books by the late John Borwein, some of them are written, co-authored with Bailey, on experimental mathematics with different titles like Experimental Mathematics, Mathematics by Experiment, The Computer is Crucible. If you go to Amazon, for example, and put in Borwein, you'll see a long list of their books. And Borwein and Bailey are real mathematicians who do mathematics for a living. And their notion of experimental mathematics is not as extreme as mine, but sometimes they reference my ideas. Anyway, they believe that after using the computer and doing lots of calculations, you conjecture a result, but they still believe you've got to prove it using the normally accepted principles. Okay, so that's not as an extreme version. Now, another person who I invoke as support for my philosophical position that mathematics is quasi-empirical is from an earlier generation. Borwein just died. I think Bailey is still alive. In an earlier generation, when I was a student, a very influential mathematician, at least to me, was Polya, a Hungarian refugee who had settled at Stanford. And he wrote a number of books and articles in favor of experimental mathematics. He would call it heuristic reasoning, and he knew a lot about mathematics history besides being a working mathematician, particularly Euler. And he has case studies. He has a 2-volume set published by Princeton University Press called Mathematics and Plausible Reasoning. And those books have many case histories of how Euler discovered something. And basically, Euler would do calculations. He would see something seemed to be the case. He might come up with a partial proof, and maybe through a series of papers, he would gradually complete the proof. And in some cases, he never completed the proof. Okay? And so Euler is working a lot like a physicist would work, according to Polya. And there's a short article which is really beautiful that I loved when I was a young student. It's in the American Mathematical Monthly. You don't have to read the big book by Polya. It's called Heuristic Reasoning in the Theory of Numbers in 1959. He gives an example of a conjecture in number theory that seems to be the case, and he proves it the way a physicist would sort of prove it. A physicist like my friend Stephen Wolfram, perhaps. You conjecture it, and then you don't find a complete proof, but you can find a probabilistic argument that makes it sound plausible, okay? And I highly recommend this little article that I found on the web, by the way. Okay, but I have a more radical view. It's true that Gauss and Euler used to do extensive calculations, conjecture results, and then try to prove them, and in most cases succeed. But I'd like to take a more radical position because I believe that one, as you can see from the theorems I proved, that you need to increase the complexity of a formal axiomatic system sometimes. And you need to do that by adding new principles. And on what basis would you do that? You know, there's no way to prove an axiom is correct, because if you could prove it, it would be a theorem, not a new axiom. But the way you justify a new axiom is the way physicists justify, say, the Schrödinger equation. You know, you don't deduce the Schrödinger equation or Maxwell's equations from Newtonian physics. They're justified by the fact that, pragmatically, because of the fertile consequences, because they explain a vast range of new phenomena that aren't treated in Newtonian physics. So I was corrupted by loving physics when I was a student, and this is my proposal. So the idea is, in other words, to put it in more romantic, poetical terms, since we've had poetical talk by a poet here yesterday. I believe in creativity in mathematics, and I believe that math is not a closed system, it's an open system. So a fixed formal axiomatic system that Hilbert wanted for all of math, yes, it would show that mathematics gives absolute certainty, but it would also sort of be a cemetery, you know, frozen object. So I believe in adding new axioms occasionally, and I've been saying this for many, many years, and of course, nobody is convinced, but in fact, not by my arguments, not by my theorems, but in fact, there are, since I've been around already for a while, I've seen new axioms prevail. One example is in theoretical set theory, a very difficult subject. I think it's called the axiom of projective determinacy, that the community has decided enables them to prove a lot of results that are conjectured but couldn't be proven, but it still doesn't settle Cantor's continuum hypothesis. So that was a new axiom that was added in my lifetime. In theoretical cryptography, mathematical cryptography, there's the problem that I think, as far as I know, nobody has shown that a crypto system is secure. Nobody's proven it. You have to use unproved assumptions that the community agrees on, such as factoring a number is slow, I think. And I think the assumptions that people use to prove that crypto systems are secure have changed as a function of time, because some of those crypto systems were actually cracked. So it turned out that the hypothesis that was used to prove that the system, to prove within quotes, the system turned out to be not the case. Now, one of the hardest branches of pure math is elementary number theory, or arithmetic. And I used to think that the Riemann hypothesis was a good example of a new axiom, because I had seen a number of papers that said they were modulo the Riemann hypothesis. Okay, that's a mathematical way of saying that they're basing the proof in the paper on an unproved hypothesis, which is called the Riemann hypothesis. But one day I gave a talk on this in a math department, and a number theorist came up to me, and he said, well, it was a good suggestion, but it turns out there are different versions of the Riemann hypothesis. You know, some are good for this, some are good for that. He didn't feel there was such a clear, compelling case that the Riemann hypothesis in the version that Riemann, the original version of Riemann, was a compelling candidate for a new axiom. But anyway, that's a field with many open problems that empirically, by doing calculations, seem extremely plausible. Like there's a conjectured result about the distribution of twin primes with a simple formula. Palya discusses this in his 1959 article that I mentioned. But nobody can prove it. But a physicist would say, well, you're graphing the distribution of twin primes. The formula fits beautifully, better and better as you go further out. What more do you want? But it's not a particularly good new axiom to add because it doesn't enable you to prove lots of other results. If it did, that would be a good candidate for a new axiom. Okay, so to summarize, since we have a lot of 3 musical events, the coda of this, I think, is that complexity is our friend because it reveals the depth of the incompleteness phenomenon, I think. And to summarize, using the notion of complexity that I've used, which is a very simple-minded notion of complexity, one way to put it is the Platonic world of pure mathematics, of mathematical ideas, has, if you use this measure of complexity, it has infinite complexity. But any formal axiomatic system only has finite complexity. Therefore, any formal axiomatic system can only capture an infinitesimal part of the richness of pure mathematics. Okay, now this is a controversial statement, but I've tried to build a case for this statement. Now, if you want to see some more on this topic, there's an interview. The way that Reda Benguerir and I became friends is that he interviewed me for that beautiful book, La complexité, vertige et promesse. I don't know if there are any copies left in the bookstore. There's also a book by a philosopher, a collection of articles, New Directions in the Philosophy of Mathematics, Princeton University Press, 1998. Tomasco died soon afterwards. It was very tragic. And that book contains essays by Lakatos, I referred to, and 2 articles of mine, one of which I sent to Gödel and was the reason that he gave me an appointment. And then I have some more articles that maybe somebody would be interested in. But another very important reference is a very recent book by my good friend Stephen Wolfram. I remember the title has the word Metamathematics very big, but it's more than that, isn't it? Okay, there were a lot of copies in the bookstore and they're all gone. So now, Stephen has as usual, has a completely new take on all of this subject. A very important new work, and he does where our paths depart is after saying that the notion of a formal axiomatic system is very important, I think, for you as for me. But one should add that your approach is based on the Rouliad and other stuff that you referred to yesterday, right? And I think there are still a few copies of a book of mine in French, Flammarion, on such topics. So I know that all of this seems very far-fetched, far from practical applications that we're all concerned with, but I want to thank you for giving me an opportunity to present these crazy ideas before you, and now I think there's going to be, if there's time, some discussion. Thank you.
Yes. Thank you very much, Gregory, for fascinating. You can sit there. I will ask Stephen Wolfram, David Chavalarias, and Hervé Svirn to join us. for the discussion. While they're coming here, I'm going to abuse my privilege as a moderator by asking you, Gregory, or making some remarks. First of all, I want to congratulate you, because when I chose the title Complexity, Friend or Foe, I didn't imagine that someone would actually give an answer to friend or foe, and you gave an answer which is actually a friend and a foe, which correspond to life, where our friends can sometimes turn into foes and our worst enemies can become our friends. The second thing is a remark or a question I will put to everyone. When you say that you chose a new path to incompleteness, and you go from self-reference, the good old thing, to complexity, well, it's great, because the solipsistic thing about the self-references in Gödel is actually the same thing as this annoying Cretan liar says, I'm lying, I'm not lying, etc. And it's solipsistic in the sense that another annoying guy, who's the priest, Berkeley, used it maybe as an example that the world is not here. By actually switching to the complexity of the world as a proof of incompleteness, you might have proven that the world actually exists. So congratulations, Gregory. The third thing, if I may, I've written a book about Gödel and Grothendieck, which is called God, Mathematics, and Madness. We had a discussion about it yesterday. I would like to ask you the permission to reproduce that anecdote if there is a new print of my book about Gödel actually canceling something big. Okay, yes. Thank you very much. And last but not least, are you the great priest of ad hoc hypothesis? Because, as you know, when I was a student, we were told never to use ad hoc hypothesis, but I have the impression that you actually like ad hoc hypothesis. So that's the first question, and then I give the floor to our distinguished guests for what is going to be, I think, fireworks of intelligence.
Yeah. Well, you know, I originally wanted to be a physicist, and I tried to be, well, I got over that at a fairly young age, but I got corrupted by reading a lot of physics. So you know, ad hoc is a pejorative remark, but if you look at how physicists actually work, they're opportunists, right? You find a principle that helps you to understand a set of phenomenon, and at first it may look very strange, and physicists will say, no, that can't be. But after a while, everyone takes it as natural. So the ad hoc turns into a contribution eventually. So I think that maybe, you know, it's nice if you can produce an airtight proof from principles that everyone agrees on. But if you can't, and if you have to use a probabilistic argument or some other more or less plausible hypothesis to get a proof, you know, Euler did that all the time. I read some of Euler's papers, not the ones in Latin, the ones in French. And he works a lot like a physicist would work. So you know, I think ad hoc sometimes can be our friend rather than our foe.
Okay, thank you very much. Stephen, do you want to comment? I have a question for you, Stephen. The incompleteness, does it actually appear in your system? And then you can comment on whatever Gregory is.
There's all sorts of things to say about incompleteness, but I think one thing I wanted to launch with a bit is Greg talked about this idea of kind of treeing out all the theorems that follow from a particular axiomatic system. One of the things that's pretty fun is to actually think about what you make by doing all that treeing out. You make this giant network of all theorems that can be established from given axioms. The question is, what is that thing that you make? It turns out that thing you make is, in the end, basically the same thing that physics makes when it makes space and space-time in the universe, which is a very bizarre kind of conclusion. But I think the first thing to think about is, what is the geometry of this thing that is made? You know, you talk about what is in principle reachable. The other question is, what does this look like, this sort of infinite object made from all these sort of mathematical atoms? And that's something that I think is, you know, first thing you might ask is, producing all these theorems, most of them will be ones that people will say, I don't care about that theorem, I don't care about this theorem. There are just some theorems dotted around that are somehow interesting theorems that people pick out and say, these are ones we actually want to care about. It's not that different from the question of which axioms you pick out to say, these are the ones that we care about, these are the ones that we want to develop things from. But I think the one thing that I've been very curious about is, we know that undecidability, incompleteness, and so on are generic properties of axiomatic systems. And in things I've done in studying simple programs, it's completely routine that the questions one asks the answers will be undecidable. Yet, in practical mathematics, mathematicians manage to go about most of their business not running into undecidability. Why is this? What is the thing that makes mathematics, as done by typical mathematicians, not keep on getting blocked by undecidability? What are they doing that's different from what we imagine that they're doing in this kind of meta model of mathematics, where they're just enumerating theorems and finding out that there's incompleteness in doing that? I think I finally understand, the answer to this question, because I've been curious about this for a long time. And I think it's really the following thing. So essentially what's happening is there is this axiomatic level. There's this level where you're looking at this whole network of theorems, you're doing things in a very formal way with axioms. But in fact, mathematics as practiced by mathematicians is operating at a much higher level. So there's an analogy. If you think about a fluid made of molecules, the molecules are all bouncing around, they're doing very complicated things, but most of what we humans talk about fluids is things about the overall motion, the presence of vortices, things like that. I think it's the same thing in mathematics. Let's say you're talking about the Pythagorean theorem. It's a thing which, the typical mathematician will understand sort of what it is. You'll be able to build on it. You'll be able to do mathematics in which you deduce things from the Pythagorean theorem. Now you say, what really is the Pythagorean theorem? Let's axiomatize the Pythagorean theorem. Well, there are, formal systems that have been built, even, programs that explicitly try to formalize things like the Pythagorean theorem. It turns out there are many ways to do it. It depends on how you decide the real numbers are set up. It depends on all kinds of things. And by the way, the actual structure, the number of iterations of the axioms that you need to fully formalize the Pythagorean theorem is very large. If you unroll the thing, it's in the 10 to the 50th, this kind of size. If you kind of aggregate things together, you'll get away with a few thousand. Okay? But so it's pretty complicated. So I think the thing to realize is that mathematicians, as they actually do things, operating at the level of the Pythagorean theorem, don't see this low-level sort of molecular scale stuff that's going on. They're operating at this fluid dynamics level. And the question is, when does that low-level axiomatic stuff poke its head up? When does it start to appear in the practical mathematics that's done? There's an analogy in fluid dynamics. In fluid dynamics, if you're looking at something like hypersonic flow, it matters what the individual molecules do. It doesn't matter in ordinary fluid mechanics because the molecules are kind of jiggling around enough that just their averages matter. So there are these weird cases, there are these sort of, but most of the time what's happening is that one's operating at the level of this kind of fluid dynamics level. That's the typical level that mathematicians operate at. I think that's why there isn't more, you then have to show that there is a continuum limit of metamathematics, basically. You have to show that when you take the limit of all these different low-level axiomatic things, that you actually get something that doesn't require you. Every time you think about the Pythagorean theorem, you can just talk about the Pythagorean theorem. You don't have to say, oh, but I have to drill down and look at all these detailed, particular, formulations that you might give. So I think that's, it's a thing I've long been curious about. I'm actually curious whether other folks here have different views about this, because I've had different views in the past about why practicing mathematicians don't run into undecidability more than they do, given how, and by the way, I should say that many famous problems in mathematics, like the Riemann hypothesis, are likely to be the reason they've been unsolved, or the Goldbach conjecture, for example, the reason they've been unsolved for centuries is probably that they are actually examples of things which are effectively undecidable, independent, whatever, of the existing axioms, and that's sort of what's being discovered there is
Stephen, since you are talking about the Riemann hypothesis, you know the famous quote by Hilbert that if he were to sleep for 1,000 years and wake up, the first question he would ask is the Riemann hypothesis proven? What would he think, what would he say if instead of saying proven, we would say, no, it has just been accepted as a new axiom? Would he be disappointed? Would he be happy? I will ask Hervé Sviern maybe to answer the question.
Well, it's difficult because I'm not in the mind of Hilbert. I would say that perhaps, but it's a history of science question more than a mathematical question. I would say perhaps that Hilbert would be disappointed, but not Gödel. In the sense that Hilbert was, as we all know, willing to get something for the mathematical foundations that is certain. And of course, we all know that it was not possible due to Gödel's theorem. But Gödel's, having proved his theorems, was more open to new axioms because he proposed himself new axioms. And in this way, perhaps he was more open to thinking that things that classical mathematicians know but are not able to prove are not something that is possible to prove inside the current axiomatic system, but needs some new axioms to be proven. And I would want to add something to what has been said, of course, about the importance of indecisible in mathematics. Of course, the majority of mathematicians doesn't need to bother with all that kind of things because, as Stephen said, it's like in fluid dynamics. We usually work with things that are not indecisible, and the mainstream of mathematics doesn't need that. But, and Greg played an important role in proving that from the Gödel's time to now, indecisible have become much more present than the time of Gödel. At the time of Gödel, the sentence that is indecisible is a very strange, weird sentence that is not something that is used in mathematics, that is really built for the Gödel's theorems. But now, and the examples that Greg explained, we have many examples of nearly current mathematics that can be proved to be indecisible. And mainly in arithmetic, for example, and the current number theory, many things that are possible to describe in a very easy language can be proved to be indecisible inside of course, the Peano formalization, but even in the ZF formalization. And the acceptation of new axioms, such as the determinacy, the projective determinacy, which is a new axiom that seems to be now accepted by the theoretician in set theory, and which is not at all obvious, is now quasi accepted because it has very important consequences inside the current mathematics. And I think that it's something that is relatively new. It was not true, let's say, 50 years ago. And perhaps in the future, we will see that many strange, because counterintuitive or axiom for which we have absolutely no intuition, such as the acceptation of some very large cardinals, for which it is impossible to have any intuition because that is something that is totally beyond our imaginations. Those very large cardinals have implication in the down-to-earth mathematics. That's strange, even in the finite. And the reason why, and that's similar to physics in this case, the reason why mathematicians will need to accept those very far axioms is that they have implication in the near mathematics. And that's something that Gödel has already foreseen, but that is probably becoming more frequent in the future. At least I think so.
Thank you, Hervé. I will ask David to comment on Gregory's talk, and I will ask you then another question. Please, David.
Yeah. So just a quick remark, because this is not specifically my specialty, but what about thinking about, if we think about mathematics that try to describe part of the world and all the consequences that we can derive if we accept some axiom on the states of the world, then if we think about the world and the physical objects and also the emergence of life in this physical world, etc., as something that creates its own phase spaces with an open phase spaces, then this means that the evolution of mathematical formalism with new actions that will be introduced to describe new phenomena or try to describe this phenomena, this is bound to also be expanded. For example, we discovered non-locality in quantum theory, so we try to develop new mathematics for that. And so beyond the probability and the question of completeness of a given set of axioms in mathematics, there's also the question about the variety of different mathematics that we can develop when we try to understand the world, and if this variety also is bound to, is it infinite? Are there like infinite number of mathematical theories that we could eventually develop when this is also the world develop and that we want to understand this world? So just to have an impression about that, about the variety of different mathematical systems that can be developed, and if this variety is itself somehow bounded, or if it's bound to evolve also with the world that is itself evolving and opening new phase spaces, as to say. So just to have this kind of remark.
Thank
I don't
you.
know if it makes sense to you.
Thank you. We'll leave Gregory, before I give the floor back to Stephen, do you want to react to what has been said? You should have the mic.
Does it work? How do I turn it on? Hello? Yes. Well, yeah, my hope is that, well, there are a lot of young people here at the university, enthusiastic, optimistic, energetic young people. I think it would be sad for them. Some of them are studying pure mathematics, and I think, or even applied mathematics. I think it would be sad for them if new mathematics isn't developed, if new axioms aren't added to mathematics to attack problems or areas that we can't even imagine at this moment. You know, I'm a great believer in creativity and the future, and if Hilbert had been right, I think it would be boring, you know, mathematics would be a closed book. I'm sure Stephen has something to say about this, right?
Yes, Stephen, you have exactly 2 minutes and 35 seconds to answer.
Okay, well, I don't know what, you know, one thing to say about new axioms, I mean, I, for example, have studied a lot the space of all possible axiom systems. And one question is, in that space, where are the ones that we care about? So, for example, if you just start enumerating axioms, start from the very simplest, you keep going, something I discovered 23 years ago is Boolean algebra, logic, is about the 50,000th axiom system, that the simplest axiom for Boolean algebra occurs at about the 50,000th axiom system that you reach. So this question about sort of which axiom systems are, well, one question is which are useful, and that's often defined in terms of which describe the physical world, but the physical world is also described the way it is because we observe it in a certain way. So it's a slightly, this question about which axioms work for us as kind of human mathematical observers is an interesting question, and I think it's quite possible that there are things like, you know, the continuum hypothesis might be something which is definitively true or not true for observers like us. So in other words, it's that in the space of all possible mathematical axioms, one can study that space. It's an interesting thing. It's this Rulliad object that I talk about. But what is relevant for us is the slices that we manage to take as observers who are like us, so to speak. And I think one of the, so there are lots of things to say about that.
Could be a closed system? So you're saying that could be a closed system?
Well, the set of all possible axiom systems is itself a studyable thing. It's kind of a meta-mathematics, so to speak. And it has all sorts of interesting properties. But this question about, okay, the question about what parts of that are interesting and accessible to us depends a lot on us. So if we started to have, if we were aliens with different, sensory perception, different kinds of structures of our minds and so on, we would conclude different things about what was interesting. So I don't think it's closed. And I think in the course of time, the only thing that's difficult is, in the course of time, we gradually expand the domain that we can talk about. As we expand kind of the paradigms that we think about in terms of science and other things, we gradually get to be able to talk about a broader set of, in a sense, axiomatic systems. Now, the thing you might say is, well, gosh, in the future, maybe we would get to the point where we expand throughout this whole Rulliad of all possible systems. The only bug with that is, in some sense, our coherent existence is a feature of the fact that we are localized in the set of possible axiom systems. If we say we encompass everything, then we no longer have, and this is probably a longer discussion, but we no longer have a sort of coherent existence. So it's kind of a be careful what you wish for. If you wish to really expand throughout all sort of possible physicses, possible mathematicses, then you don't have, there's no sense in which you have a coherent thread of existence.
Thank you. We still have like 8 minutes to go. I want to ask you also a final question. It's more kind of almost a philosophical or sociological question. When we talk about incompleteness, about the impossibility to prove the coherence of any rich enough system of axioms, what would you say, what you answer to those people who use this as to discredit mathematics, in particular science in general, and to introduce metaphysical themes in mathematics via this, what they see as kind of a door ajar, an open door, because of incompleteness and coherence. I ask this, I'm very much interested in your answer because it's part of what I teach here. I don't like this idea of this door being ajar and letting metaphysics enter the field, but I would like very much to hear you distinguish guests about this. So what would you say to people who discredit math and science because of incompleteness, being incompleteness of Gödel, of Chaitin?
Okay, I have a perhaps short thing to say.
We had this discussion yesterday.
Yeah. Well, so I think that computational irreducibility is kind of a lower level concept than incompleteness. It's a simpler concept. It's a concept that you can't know the answer except by going through each computational step. Now, people have gotten the idea that science is a story of being able to jump to the answer. That's the way that sort of the science from the 1600s, kind of mathematical formula-based science, that's the way it works. It allows you to just say, this is going to happen in the world, we can just write down a formula and say that. Computational irreducibility says that's not how it works. You have to go through all these steps to get to that answer. And so it looks, from the point of view, you might say, the presence of computational irreducibility, which is a sort of junior version of incompleteness, is a statement that science no longer works. It's not really that statement. It's a statement that it is true that to claim that you can immediately jump to the answer, that's not correct. And by the way, we should consider ourselves fortunate that one can't just jump to the answer, because all of the time that we experience, going through life and so on, is all about this progression of as I see it, computational irreducibility. If we could just jump to the end and say, and the answer is 42, it would make much more meaningless the process that we go through in experiencing the passage of time. So it's not a bad thing in a sense that you can't just jump to the answer. But I think that to me is it's a real thing that you can't just jump to the answer. In some ways, science, as people have perceived it in the last, 50 years or so, has kind of perhaps overreached in its statement that you can just jump to the answer. I think you can't, and this is, that's a way to sort of see that, and Gödel's theorem was the beginning of that process. That would be my response.
Gregory, people can use your word, Gregory, to discredit maths and science.
Well, on the other hand, in spite of Gödel and all the incompleteness results, mathematics in the last 100 years has been progressing remarkably. These pessimistic-looking results fly in the face of the actual reality, which is pure mathematicians are very happy, and every now and then they celebrate a major new triumph. So,
you might argue that the reason they can be successful is that they're carefully navigating what they're studying through all these horrible things. And that's one of the questions, is that what's happening? Is mathematics just picking those few paths that avoid incompleteness? Or, as I now think, is it a more generic phenomenon that you can do a mathematics at a sort of human level that does not look down to this level at which incompleteness is generic?
Okay, thank you. Hervé?
I think that your question could be extended to science in general. It's not only mathematics.
Yes.
Are indecisibles discrediting mathematics, but are, in general, the limits that science has discovered discrediting science? And that's the subject of my book, Les limites de la connaissance. When I wrote it, many people said, okay, but writing this book, you are going to discredit science because you prove that science has limits. But that's a little bit naive to think that science can have the answer to any question and that everything is subject to easy modeling, giving immediate answer. That's not true. And I think that the very fact that science is able to show what is feasible in this old way of seeing science and what is not feasible like that, and that it is science itself that determines the limits, is an achievement that is astonishing. And of course, far from discrediting science, it's something that it proves at the point at which science is efficient, I think. And the only thing that it proves is that the universe is not so simple that we would like it to be. It's much more complicated.
Thank you very much. David, do you have a reflection?
Yeah, just to continue your reflection, I think this is really interesting because, for example, there is something that really characterizes human, or that is very specific to human, is that we know when we don't know. Contrary to most of animals, very few primates also know that. So, if you look at this in mathematics, this is actually absolutely not discrediting mathematics of science. It's just that it is really a specificity of human culture that we are able to say, here we don't know, here we know. Maybe we will never know, so we have to organize ourselves to not go to that direction or go to knowing this. So yeah, I think that this kind of theory is really important because it's allow us to better know about ourselves, our predicting capacities. And also just to add something that here we are talking about, when we are talking about this mathematics theory, we don't talk about the position of the observer and the time scale and what we want to do with those mathematics. And so sometimes there is something that we cannot prove because we cannot prove asymptotic behavior, but we can more or less have an idea about the behavior at its infinite times. And this is very important. So even if you know that you cannot prove an asymptotic behavior, so if you can prove something or have an approximation of the behavior of something in 1,000 years, it's enough, to develop the societies and civilization, etc. So mathematics is a beautiful things in this kind of purity where you want to go until the infinity, etc. But still, when you know that you don't know, there is still domain that is still useful because maybe you know something about short time scales or more middle time scales, and this could be enough just to develop your civilization and culture. So this is two remarks to say that still, yes, this is not at all something against science. On the contrary, I think it's a proof of science maturity to know these kind of things.
Thank you very much. And when Socrates said, "The only thing I know is that I know nothing," we don't despise him for saying that. In fact, we admire him for saying that. So when science says, these are my limits, we actually admire scientists for being humble about that. Well, I have to thank my friend Reda Benguerir, who assembled this beautiful set of distinguished guests. I have to thank you all for having been here. Thank you very much, and let's meet again tomorrow.